Hi, this is part 2 of 1.02 Behavior of Gases. So you might have noticed with all this copy paste that I have different fonts. And if that is not what you like, you can go up here, so highlight everything that you want, and you can just change it to be the same font as well as the same size. So that's up to you because I know some people really like to make sure everything is the same font. All right, but when I did that, I would still go back and I would bold my vocab words. That way they're easier to see when you're looking for them. All right, let's go to the next slide. It says pressure is commonly discussed in terms other than pascals. So Evangelista Torricelli invents the barometer to measure the pressure of a gas. You may encounter other units of pressure because atmospheric pressure was measured with a mercury barometer. You may see pressure measured in units of millimeters of mercury. So in other words, of pascals, the unit would be mm, millimeters, Hg, mercury, which also is called torr. And this unit was named after Evangelista Torricelli, who elucidated, well, there's a big word, in other words, came up with the principle behind the barometer in 1600. All right, so here we have this table of all the different possible units of pressure. So you might remember that I mentioned PSI, pounds per square inch, earlier in the last video, because that's what we tend to use here in the United States, especially with tires. So again, I'm just going to grab a screenshot of that, and I am just going to put it right in here in my notes so that if I need it at any time, there it is. The behavior of gases. Although Pascal is the SI or metric unit for pressure, different units are used in different fields of study. It's important to be able to convert between units of pressure. Explore the table of different units of pressure. Note that millimeters of mercury and torr are the same unit. It's kind of like if I want to change inches to feet, or feet to miles, or miles to kilometer. That's what they're talking about. So how you do a conversion, which is going to come up later more in the units, or maybe even just later in the semester. But you start with what you are given. So it says a gas has 3 atm or atmospheres of pressure. What is its pressure in millimeters of mercury? So I write down what I know, and I make it a fraction over 1. Then I do a conversion fraction. So if you remember in math class, 5 over 5 equals 1, 10 over 10 equals 1. Well, ATMs over ATMs, they cancel out 2. So basically you're putting 1 ATM at the bottom to get your unit to cancel. And 1 ATM from this chart, 1 ATM, is the same as 760 millimeters of mercury. So the ATM unit cancels off. We have 3 times 760 equals 2,280 millimeters of mercury. If you're feeling a little, eek, I'm not quite there yet with these, that is okay. All right, we will do more of those problems before it's really on a test. Gases are compressible. So balloons and soda bottles expand to the contraction of air at colder temperatures in a refrigerator or freezer. That's why when you have a water bottle, if you want to freeze it, you don't fill it all the way to the top, right? It will break the water bottle. Gases are the same. They are going to expand and contract based on temperature. So if you take a balloon and squeeze it with both hands, what happens? The balloon probably shrinks or compresses. As you increase the squeeze on the balloon, you increase the outside pressure on the air inside. Because the air inside is mostly empty space, the volume shrinks and the molecules get closer together. This is a feature of gases. They are compressible. Fill another balloon with water and tie it off. Now try squeezing it again. Do you need to squeeze the balloon harder or more softly to get it to shrink? Does it shrink at all? So think about that. Picture a water balloon in your hand and how that feels versus just one filled with air. You will probably find that if the balloon shrinks at all, getting it to shrink requires much more pressure. In contrast to gases, liquids are not as compressible. Liquids are used in hydraulic lifts, such as those to lift cars in service garages, because of this factor. All right, so let's add on here. Let's go ahead and add on here, gases are compressible. So in other words, there is empty space between the molecules so they can get squeezed together. You might have noticed when I take notes, I tend to write things in parentheses to kind of explain things or just write them in more common words. Volume of a gas changes with temperature. Carefully place your air-filled balloon over a heat source, such as a hairdryer, set on low, and note the size of the balloon. Okay, or think about if you've ever seen a helium balloon outside in winter. When it goes outside and it's cold, it shrinks. So now this one's saying we're heating it up, so you may see it as the balloon warms, it gets bigger. Specifically, as the temperature of the air inside the balloon increases, the volume of the balloon increases. So we have a good comparison there. We have as, this is a huge one with gas laws, as temperature increases, the volume of a gas also increases. And we should probably go back and write that one for the pressure, right? They didn't flat out say it, but yeah, it's that same relationship thing. So as pressure increases, the volume of a gas decreases, right? When we squeeze it, it's getting closer together, okay? When the temperature increases, think about when you are really cold. When you're cold, you're like, you cuddle up. When you're really hot, you're like, whoa, spread out. So when the gases get warm, they spread out too. And it has to do with because they have more energy and they move faster, not because they just feel yucky and sweaty. All right. Can you tell it's late in the evening? You get comments like that. Take that same air-filled balloon and place it in a freezer for a while and note the size. You may see that as the balloon cools, it shrinks. Specifically, as the air inside the balloon cools, the volume gets smaller. Another behavior of a gas is that the volume changes directly with the temperature. So in math class, the fact that when one goes up, the other one goes up, that's called a direct relationship. Use the particle simulator to explore the relationship between temperature and pressure as the gas is heated and cooled off, and observe the motions of the particles. All right, so we can heat it up. I guess let's add a lot of heat. And what do we notice is happening? We definitely see some movement. And I wonder if I just don't have enough. Well, the pressure increases as the temperature increases. So we'll just keep watching that for a little bit. Maybe I'll add some more in there and see if we can actually get it to work for us. But like I said, when you increase the temperature, the molecules are moving faster. And as they're moving faster, right, they're going to be bumping more and there's going to be more pressure. So that is a good one to add to our notes as well. So in case you didn't catch it, this unit about gases is a lot about relationships. Oh, there we go. We can finally see that the pressure is going up. So what happens to the pressure as the temperature goes down? Okay, so if pressure increased and temperature increased, if we decrease pressure, what's going to happen to the temperature? It's going to go down. What happened to the speed of the particles as they were heated? Oh, there, finally we can see it. They go faster and they collide more. And cooling, what do you think that would be? They are going to move slower. Yeah. All right, so let's just add in as temperature increases, molecules move faster. As you change the amount of gas, you change the pressure. So now we're talking about how much we have. Consider pumping a bicycle tire or ball. The air fills the tire or ball to the same fixed volume, after which the volume does not change. However, if you continue to pump air into the tire, the pressure measured by the tire gauge or pump gauge increases. Can you explain what's happening? Okay, so pause and think. Think about a bus. Think about how it would feel inside if it was just you versus if there was 100 people packed in. As you continue to pump, you put more air in the ball or tire. However, the volume of the tire ball is fixed by the strength of the material. So the tire can only get so big. Okay. So the amount of air increases, so does the pressure. So that's why when you have a flat tire, you don't have as much air, right? But when you add more and more air, the tire feels much harder because the pressure increases. So the amount of air increases, so does the pressure. So as the amount of gas increases, pressure increases. By contrast, if you open the valve, the pressure falls as the air leaks out. Therefore, at constant volume, pressure is directly proportional to the amount of gas. Ooh, remember that? Directly proportional. So in math, when something is directly related, when one goes up, the other one goes up. When one goes down, the other one goes down. The opposite of that is inversely. So inversely would be this first one. When the pressure increases, the volume decreases. And you're not going to be tested on those two words. I just wanted to throw them out there. Gas molecules can move from one place to another. This wouldn't be so bad if it weren't for that darn diffusion. Cut an onion at one end of a large room and either go to the other end of the room or have someone sit at the other end. What happens? You or the person opposite the onion will eventually smell it. Why? The molecules that make up an onion's odor move randomly through the air in all directions. Remember we talked about how a gas is going to spread out and fill the entire container. However, there's a net movement or total movement of the molecules from an area of higher concentration, the onion, to an area of lower concentration, the opposite side of the room. This type of movement is called diffusion. Gases as well as liquids diffuse. Diffusion allows you to smell what's cooking in the kitchen from somewhere else in the house. All right, so I'm just going to copy that. So gases and liquids are going to diffuse. Of course, we want our definition. And diffusion equals, there's my definition. I'm going to make it bold. Oops. The process in which atoms and molecules move from an area where they are more concentrated to an area where they are less concentrated. What is natural gas? Natural gas from furnaces is odorless, so gas companies mix a smelly gas called T-butyl mercaptan with it. That way, if there's a gas leak, both gases diffuse from the area of high concentration, the source of the leak, to areas of low concentration elsewhere in your house, so you can detect the leak by smelling the mercaptan. If you ever smell gas in your house, you need to leave and then call. Do not turn on any light switches. Do not call while you're in the house because it can cause a spark. Even though you're like, really? I've called like 100,000 people on my phone and it's never sparked before. It's not one you can necessarily see. It's a static charge. So, safety first. Chemists use a standardized temperature and pressure. As mentioned before, the volume of a gas is influenced by temperature and pressure. Chemists recognize the need to have a specific standard of temperature and pressure so they can be consistent in doing their experiments. Because you need to get the same answers in summer as in winter. You need the same answers if you're here or if you're in Australia. So the chemists came up with this standard. This standard was internationally agreed to have a temperature of 273 K. K stands for Kelvin, which is a measurement of temperature. 0 degrees Celsius, and remember we use Fahrenheit here in the United States, but it's science. So 0 degrees Celsius is the same as 273 degrees Kelvin, but you don't say the degrees, you just say Kelvin. So that's the standard temperature, and the standard pressure is 1 atm, which is 101.3 kilopascals. The International Union of Pure and Applied Chemistry, the IUPAC, set the standard for pressure units in 1999. Okay, they set that before that because I went to high school before then and they had it. Whatever. These conditions of standard temperature and pressure are abbreviated as STP. So, STP equals standard temperature and pressure. Okay, so that's what scientists are comparing their experiments to in order so that they can be replicated around the world. So freezing water is 0 degrees Celsius, which is 32 degrees Fahrenheit. Your body temperature is about 90